Assalamualaikum and good day everyone. Today we're going to cover chapter 5 frequency response and Bode plot part 3. Previously I have shared chapter 5 frequency response and Bode plot part 1. Okay, so without further ado, let we proceed. Okay, the outline, the application, introduction of filters, type of filters, ideal filters, practical filters. So we will go through this later on. So introduction to the filters. Okay, what is filters? Filters is actually a spatial network. Okay, that in brief, in concept is that we allow some frequency to pass through while we are blocking the other frequency not to pass through. Okay, so that is the layman term. Okay, but here that we see the word here, spatial network. Filter is a spatial network purposely designed to block unwanted frequencies. A filter is typically designed to pass and stop some frequency region, like I told you. So these frequency regions, okay, the one where we stop, we can call it as a stop band, and the one that we allow it to pass, it is a pass band. So this is the frequency range. Okay, so if you see in this system, we have a transmitter, we have a filters. Okay, and when we transmit the signal, for example, a cos omega t, the signal we send wirelessly, and in free space communication or in any other type of communication, there is noise introduced to our signal. The noise is something that we unwanted and cannot be avoided because it's there naturally. Okay, so there is a noise NT added to our signal. So end up our signal while transmitting is adding up with with a noise, which is A cos omega t plus NT, which is this is our noise. And then when the signal arrive at our transmitter, okay, this signal mixed up with noise have to be filtered out, okay, because we don't want the noise. Okay, that's why we have filter here. Okay, the filter will remove this unwanted component, which is the noise, and only allow the one that we want, which is the A cos omega t. As you all know, this actually the modulated signal, the signal that we modulate to our information signal so that it can be transmitted wirelessly over a distance. Okay, filters. Okay, passive filters network consists of passive elements. Okay, such as your inductor, capacitor, and a resistor. Active filter network consists of active elements such as op-amp and transistors. So easy, if it's active filters, okay, it is something that active element requires powers. Okay, so our discussion only cover on passive filters. Okay, so you don't have to know about active filter network. Okay, we only consider passive, which is consists of our inductor, capacitor, and resistor. So this is your input. Okay, this is your input, and this is your output network. Then you have passive filter in between with R, L, and C component inside it. These together construct the passive filters. So the frequency, like I told just now, we have stop band and pass band. Okay, stop band is actually the frequency range, okay, at which the output is significantly attenuated. Okay, attenuated but not totally removed. Attenuated. This is exists in practical filter. So stop band is actually the range of frequency that we don't want, and this is being attenuated. In contrast, pass band is the frequency range that we want, okay, to pass through, and there is little attenuation, means we we want the signal to pass through. That's why there is little attenuation. The cutoff frequency is defined as the boundary between pass band and stop band. So we will have this cutoff frequency. So this cutoff frequency exists between our pass band and stop band. They define the criteria for our filters. Okay, so don't worry if you don't understand. We can we will cover later on as well. So this is the ideal filter. Okay, this is the ideal filter. If you can see, this is our low pass filters. Okay, low pass filters. So if you see, this is the gain versus omega. So because this is low pass frequency, low pass filter means it only allow low pass signal to pass through and will block the high frequency range signal. So here you can see this is omega C. Any omega that is below this omega C will be allowed to pass through. So the range at which the signal allowed to pass through, we call it as pass band. Any frequency greater than omega C, frequency range, okay, ranges of frequency that is not allowed to pass through, okay, is fall within this stop band. So in ideal filter, you can see this, there is a sharp cutoff frequency, means totally solid below than omega C will be allowed, and totally exactly after omega C, above omega C will be blocked. So this is not practical in real life. We don't have this kind of ideal filters. Okay, we have practical filters, and you can see here in this is your gain, this is your phase versus omega. Okay, you can see the linear phase change from zero, from the start origin is not exactly zero, depends. Okay, from origin here until omega C, you can see there is a drop of negative 45. Okay, 0 to negative 5. So this is our negative phase change. And then after that, further it will go to 90 degree. Okay, so we will have a linear phase change, okay, in the ideal filter. Next, so you have seen that actually in ideal filter we have a sharp cutoff. However, we don't have this filter in our life. We have practical filters. Okay, so in practical filters, there is actually exists a transition band. Okay, we can call it transition band or we can call it a transition region, depends. Okay, it's just as long as you understand the transition region, where is actually there exists between this pass band and stop band. Okay, where there is gradual drops. Okay, there is gradual drop. So here you see this is V, and this is V over square root of 2. Okay, okay, you can see here V over square root of 2. So try to times with try to 20 log in bracket 1 over square root of 2, you would have negative 3 dB. So, okay, so here will be negative 3 dB. This one you can convert to dB scale, 20 log in bracket 1 over square root 2. So here is, if it's in dB scale, is negative 3 dB, a drop off from 0 until negative 3 dB. So this one let's say this, we take it as 1, okay? Let's say this is 120 log 1, it will be 0, okay? In decibel scale. So this, if it's in decibel, it will be 0, and this would be negative 3 dB. However, this value is not fixed. To make it simple, we assume, let's say this is 1, okay, for your understanding. So the cutoff frequency is at which the gain has decreased by a factor of 0.707. Okay, if you can see, is 0.707 is actually equals to 1 over square root of 2. Okay, from its maximum value past band gain. Okay, so this is omega c. Okay, omega c is actually the value, the frequency at which the gain has decreased by a factor of 1 over square root of 2. Okay, in terms of power, the cutoff frequency is at half the maximum power of negative 3 dB point. So this is in terms of power. Okay, so this one is gain. Okay, make sure you're able to differentiate that. Low pass filters. Okay, for low pass filters, we only allow low frequency range to pass through. In practical filters, this is the shape that we are going to have for our low pass filters. So this magnitude, Hj omega magnitude, means always positive. So you can see here is 1, and this is your pass band. Okay, if you see this green box, okay, this one is actually the ideal filter, the ideal low pass filters, which we don't have in real life. What we have is actually the practical filter, which is this one shown by the red color. This is the practical low pass filters. Okay, the practical filters also can be referred as non-ideal. Okay, the ideal, of course, the green one. Okay, so while this is our pass band region, this is our stop band region. And this omega c is actually the value where the gain is reduced by a factor of 1 over square root of 2 here. Okay, 1 over square root of 2. Ideal magnitude plot of low pass filter showing pass band and stop band separated by cutoff frequency. Okay. In contrast, high-pass filters allow frequency above the cutoff frequency to pass through and block the lower frequency region. So this is your ideal high-pass filter, which we don't have in real life. What we have is actually the practical high-pass filters, which also can be said as non-ideal high-pass filters. So below the omega below the omega c cutoff frequency, the signal is being attenuated. Okay, attenuated. And this one, the frequency above the omega c, above our cutoff frequency, will be allowed to pass through with little attenuations. Okay. Next is the band pass filters. In band pass filters, it will allow certain band to pass through, and it allows the other frequency range not to pass through, means it blocked the other frequency range. So you can see this is our band pass filters. So this is your ideal band pass filters, ideal band pass filter, where we actually have two cutoff frequency, which is omega c1. Omega c1 is our low cutoff frequency, and then we have omega c2 as high cutoff frequency. So here at omega c1, okay, where the gain reduced by a factor of 1 over square root of 2, it's going to attenuate the frequency below omega c1, not from to pass through. Okay, it will attenuate it so that it won't pass through. And at omega c2, any frequency range above this omega c2 will be attenuated, not allowed to pass through as well. So both of these is the reduction by 1 over square root of 2. Okay, and in between omega c and omega c1 and omega c2, there is range of frequency that is allowed to pass through. So the frequency range that allowed to pass through, we call it a passband. Ideal magnitude plot of bandpass filters showing passband and stopband separated by two cutoff frequency. So as you can see, as you can relate from previous explanation, this is the ideal bandpass filters, and this is actually the practical bandpass filters, which is the non-ideal bandpass filters. Similarly, in bandstop filter as well, it allows certain frequency to pass through and block the other frequency not to pass through. Okay, in bandstop filters, it only stops certain band and it allows the others. Okay, so you can see this is actually the green one show the ideal bandstop filters, which we can have two, and it only stop the frequency in between, which is our stop band frequency range. Okay, so again the same, we have omega c1 and omega c2. At omega c1, any frequency less than omega c1 will be allowed to pass through. Again, omega c1 is frequency at which there is a reduction of 1 over square root of 2 from the maximum. Okay, the maximum not necessarily be 1. Okay, don't assume, okay, unless it's stated there is 1. And then omega c2 is actually the frequency, cutoff frequency at which the signal above the omega c is allowed to pass through. Okay, again there is a difference of 1 over square root of 2. Okay, so this is your cutoff frequency. Bandwidth of the filters. Okay, the bandwidth of filter is defined by as the range spanned by its passband. So bandwidth is actually the range that is covered by our passband. Means that bandwidth is the operating frequency range, the operating frequency range that the system is working on. Okay, so we don't consider the one that is not working at that frequency range. Okay, so if you can see here, let's say consider this graph. Okay, we have two stop band, one at the left, one at the right, and we have this passband. So the bandwidth at which the filter is working and covered by passband, this is our bandwidth, which is omega c2 minus omega c1. The higher frequency cutoff minus the lower frequency cutoff. Okay, the difference is the bandwidth. Okay, the end. Please try this. Okay, please try this exercise. Okay, please try this. We can try discuss in our next class. Okay, if you have problems. With that, we finish the class. Okay, thank you very much. Assalamualaikum and have a good day.